So I'm not going to do all of the examples shown in this question, but I will do a few, provide you the guiding principles to be able to answer the rest on your own. So as I discussed in an my voice is changing because I'm going through puberty. So as I discussed in an earlier video linked to in the description below and floating over my head somewhere, when naming an ionic compound, which is a compound made of one or more metals bonded to one or more nonmetals, the way you do that is a little bit different from the way you name molecular compounds, which are compounds containing all nonmetals. For ionic compound, we begin by just writing down the name of the metal, the first ion, followed by the name of the second ion, with one additional sub-caveat there. Anytime the metal, the thing on the left, is in the D block of the periodic table, we also have to add Roman numerals to its name in order to designate what charge or oxidation number that metal has in that compound. Now, we do not do that Roman numeral thing for molecular compounds. Another thing for this is that when naming ionic compounds, you never use di, tri, tetra, penta, any of those prefixes. You use those exclusively for naming molecular compounds. Now, you might ask why? Why the inconsistency? My answer is, I don't know. I didn't invent this stuff, I just teach it, okay? Let's start with the easy ones, this compound right here. Now, this is a compound that is the one exception to the rule that ionic compounds are only made of metals bonded to nonmetals. You'll see looking at this that these are all nonmetals. However, this is the one exception that I will teach you, my students at least, that has all nonmetals and yet is an ionic compound. Why? Because NH4 in real life is an ion of the many polyatomic ions that I require you, my students, to memorize that has no metals in it. It is called ammonium. Thus, for the left part of the name, I will write down ammonium. What is the name of that? Well, that element on the periodic table is chlorine, but when you place it into an ionic compound, so it's on the right, that's our nonmetal partner, we call it chloride. So the name of this compound is ammonium chloride. All right? Now, what about this molecule? Well, this metal right here is called cesium. You'll notice that cesium is in column 1 of the periodic table, which means that in a compound, its charge is always +1. Because it's not in the D block where charges can sometimes vary, we do not place Roman numerals in the name. We only do that for elements whose charges or oxidation numbers can vary, which is by and large the elements inside the D block of the periodic table. Because cesium is in column 1, it's always +1. We just write down cesium, the first half of the name. What is NO3? Well, NO3 is one of those polyatomics I require you to memorize. It is called nitrate. So this compound's name is cesium nitrate. How about here? Well, you'll notice that the first element is an element in the D block. Its name is iron. And because it's in the D block, we're going to have to lay down a set of parentheses in order to identify the charge of this specific iron, because iron can exist in multiple different charges or oxidation states. Let's worry about figuring that out in just a moment. For now, let's move on to naming this thing. What is CO3? Well, that is one of the polyatomic anions I require you to memorize. Shown on this list here, it is called carbonate, and it has a -2 charge. That charge, the -2 charge on the carbonate, helps dictate what the charge is on the iron. So if I have an iron cation going together with a carbonate anion, and you can see they're stuck together here 1 to 1. There's not 3 irons and 2 carbonates or vice versa or anything like that. They just go together 1 to 1. If carbonate here has a -2 charge and it gets stuck together 1 to 1 with the iron, what is the charge on the iron? Yeah, it has to be +2. So this is iron 2 carbonate. I place the 2 in Roman numerals there to indicate the charge of this specific iron, which actually has a different formula than, say, iron 3 carbonate, a completely different compound with a slightly different formula. Make sense? Good. Let's go on to this one. This is an iron stuck to 3 of these things. Again, because it's an iron in the D block, I'll lay down its name with a set of parentheses that we'll fill in just a moment. What is the name of this thing? Well, that is a polyatomic ion that I require you, my students, to memorize called cyanide. And as you can see in this chart, it has a -1 charge. Now, in this case, I've got 3 cyanides that each have a -1 charge. So the total charge ebbing off of all of them together is 3 times -1, or -3 total, okay? So -3. So what does the charge of the iron have to be in order to cancel out that -3? It must be +3. So this is an iron 3 cyanide as opposed to an iron 2 cyanide, which would have a different formula and actually in reality be a completely different compound. Another shortcut for doing this is to look down at the subscript here. As it turns out, the subscript here, if you pull it up here, reveals the charge of this atom right here. The implied subscript beneath the iron is 1 because there's no subscript written. So anytime you don't have a subscript written, it's an implied 1. If you brought the 1 up here and slapped a negative to the left of it, that would reveal the charge of the partner right here. So each cyanide is -1. That kind of cross work for being able to identify the charges doesn't always work out all of the time. It doesn't work, for example, in this case where I have a -2 here and a 2 there. If I just did this crossing thing, I would assume that this was a -1 and that was a positive 1, and that is not the case. So anyway, those are the names of some of these compounds, and hopefully that all makes sense. Yeehaw!